restricted sum would be 1 over 5 of k. So here phi is a Euler totient function, and this sum is restricted over the integers whose smallest prime factors are in the arithmetic progressions. So this formula is like the prime number theorem in the arithmetic progressions. Then Dawsey, so 3 years ago, Dawsey generalized the lattice formula to the Galois extensions. So here are some notations. K over Q is a finite Galois extension, and G is the Galois group. And the bracket K over Q over script P is the Artin symbol. So Artin symbol is just an element in the Galois group, which corresponds to the Frobenius map. And K over Q over small p is a collection of the Artin symbols for the script P 9 over small p for unramified p. And this set is a conjugacy class in the Galois group. And Dawsey, she proved that for any fixed conjugacy class, say the following restricted sum is would be the Chebyshev density. So here the restricted sum is over the collection of Artin symbols equal to the fixed C. And then a lattice formula is a special case of Dawsey's formula if we take the K to be the cyclotomic field and say the conjugate class of L. Second, Sweden and Wu generalized the Dawsey's result to number fields. Last year, Kuro, McDonald, and South, they generalized all those results to the natural density. So here are some notations. So P is a set of all primes, and S is a subset of P. Delta of S is the natural density of S. So they proved that if S has a natural density, then the sum which are restricted over the integers whose smallest prime factors are in S, then the sum would be the natural density of S. So here are some remarks. First, their work is actually over arbitrary number fields. Here I just write down the case for the rational field. Second, if we take S as an arithmetic progressions, then we will get a lattice formula. Thirdly, if we take such kind of S, then we can, by the Chebyshev density theorem, we can get Dawsey's formula. So natural density is quite general. Now, my goal is to generalize all those results in a different way. So here, let's look at some basic observation. First, we know that Juillerat series of the Mobius function is the reciprocal of the Riemann Z function. and the limit of this reciprocal to the one from the right side is just 0. So we know this is the prime number theorem. And the observation is, if we replace the numerator 1 by a function which is absolutely convergent and s equals to 1, then the limit is also 0. So now, if we write down the Juillerat series expansion for this fraction, so a natural question is, do we still have a lattice formula? So in other words, what if we replace the Mobius function by other arithmetic functions? So that's my question. In general, the answer is no. For example, you can consider this function. But for many interesting functions, the answer is yes. So here are two examples which I did last year. So the first example is the Neuer function, and the second one is the Ramanujan sum. So here are their Dirichlet series. So from their Dirichlet series, we can see that those two functions are the Dirichlet convolutions of the Mobius function and some good arithmetic functions. So my goal is to study the general arithmetic functions. So that's what I did this year. So here, A is an arithmetic function which satisfies the first term is 1 and satisfies this convergence condition. So this convergence condition just means is just a guarantee that the Dirichlet series of A is absolutely convergent to convergent and s equals to 1. And if we have those two conditions, then we can get the following analog of a lattice formula. So here, I mean, we can replace the mu by the mu convoluted by an A. So here, mu star A is the Dirichlet convolutions of A, mu and A. And for the previous two examples, actually, it's very easy to verify that they satisfy this condition. And then an interesting corollary is under a slightly weaker condition, we can replace the denominator n by phi of n. Phi is a Euler function. So in particular, we can get the following two functions, two formulas. So here, say sub n of m. So here, this is the Ramanujan sum. M is fixed and n varies. So those two formulas refines Hardy's formula in about 100 years ago. It's just like what Aladi did. Okay, so now let's look at some examples. So The first example is this function lambda. Lambda is a multiplicative function which is bounded by 1 and takes values -1 and every prime number p. Then for such an multiplicative function, then we have the following, we have the Allardyce formula. But by the way, I also call the Kuros formula as an Allardyce formula. So, so here are some examples for lambda. So for example, we can take lambda as the neural function, -1 to the omega of n, and then -1 to the a of n. So here, omega of n is the number of distinct prime factors of n, and a of n is such additive function which was introduced by Allardyce and Erdős in 1977. And actually, -1 to the a of n is the first example I studied. Okay, the second example is the following formula. So here, the restriction is the same as Allardyce formula. And the point is the mu of m. And so this condition, it means that m is fixed. This condition means that n has to be co-prime to m. So this formula is my favorite one among Allardyce formulas. Okay, the third example is that we can replace, we can consider the multiplicative functions that are near to n. So near to n means that and the prime place g of p is very close to p. So then we can take the denominator as g of n. So here are some examples for g of n. So first we can take the Dedekind Puisy function and also the sum of divisors function and the normalized sum of divisors function for the power k. And when k is 3 and 7, this function is related to the E8 lattice and the E16 lattice. So, and also the last example is we can also take the R4 and R8. So here Rk of n is the number of ways representing n as k as a sum of k squares. So for R4 and R8, actually we have the following explicit formula. A conjecture is that for this formula, actually we can replace mu by other good arithmetic functions like the neural function and the Ramanujan sum. So finally, I'd like to talk about some conjectures. So, in previous examples, we only consider mu of n. So how about the m-fold convolutions of the Mobius function. So we know that this differential series is 1 over zeta of s to the m to the power m. So m is greater or equal than 2. So in the past, in the previous examples, m is just 1. So that's they are essentially different. So my conjecture is Aladin's formula should also hold for those functions. So for example, it should also hold for the following 3 functions. So here, lambda is the newer function, and then d of n is the divisor function. More general, we can also consider the positive power. So here m is just the integers. So you can also consider the positive power like the half, but it's still open. So I think it's very challenging. The second conjecture is that we can extend, we can generalize the lateral density to the relative lateral density. So here, P is a set of some primes, not all. So before P is all primes. So then the angle bracket of P is a multiplicative semigroup generated by P, and S, we say S has a lateral density in P if the following limit exists. So then if the reciprocals in P, the sum of the reciprocals diverges, and if the subset S has a lateral density, then I guess we have the following Aladin's formula. So here, the point is P is a set of some primes, not all. And a remark is if S equals to P, so then delta P of P is 1. So then this is a result in Terry's Tao's papers. So, so this is like a hybrid of Tao's result and Aladin's result. Okay, that's the end of my talk. Thank you for listening. Thank you.
Thank you. Questions for the speaker?
I want to ask probably one.
Oh, okay.
Yeah, I'm just curious. Something first is great talk. Second, I'm just curious. Like in the all this formula or all this formula, if you replace the smallest prime by the let's say next smallest prime in the set S or the largest prime in this, I mean, is the result going to follow similar or there's some difficulties will come?
Got it. That's a good question. So actually, for the if we restrict the sum over the largest prime factors, then actually Aladin did it in his in one of his papers. He also has a formula, but it's not so did. So actually, it's related to the saves. So, but for the second smallest one, I didn't see such result. So that's a good point.
That's my curiosity. I'm done.
Okay. Oh, as there's a question in the chat room.
Yes.
Okay. So you mentioned that the original was equal to the prime number theory.
Maybe someone else. Let me read out. So
Okay.
the question from John Grantham. So John asked that you mentioned that the original result was equivalent to the prime number theorem. Are there similar equivalencies for other results?
For other results, I guess he means that if the prime number term is equivalent to the identities for other arithmetic functions. And so actually, I proved that the prime number theory is equivalent to the lower function. So in my first paper, I proved that the prime number theorem is equivalent to the formula for the lower function, but I didn't prove the result for the Ramanujan sum. I guess it should be equivalent to the formula for the Ramanujan sum. But I didn't do it because at that point I was thinking about the general the general arithmetic functions. So it looks like it's very hard. Okay.
Well, for example, is Aladi's result equivalent to Dirichlet's theorem?
There is a theorem. Actually, I'm not sure. So because he proved this formula by Dirichlet's theorem, but I'm not sure if we can prove Dirichlet's theorem by Aladi's formula. So that's a good question. Yeah.
I have a question, if I may ask.
Go ahead, please.
Yeah, so I'm just curious that what about upper density? So you have considered this positive natural density. So have you also considered about upper density of this set of primes?
What density? Sorry.
Upper density. It's like a lim sup of x goes to infinity, and in the numerator, the set you are considering the collection of prime, that is a capital P, and in the denominator, it's all the primes less than equal to x.
Okay. So you know this. So sorry, I never heard that density, but that's a good question. So I think the point is, so that's the other direction. So it's like if that density equals to the natural density, if they are equal, then then we should have the similar formula. So, okay, did I answer your question?
Yeah. Yeah. No,
Maybe we can
okay.
discuss more in the chat room.
Yeah. Thank you.
Yeah. Sure.
Okay. So I think we need to get ready for the next talk. So let's thank the speaker again for an excellent talk.
Okay. Thank you.
Okay, so we're going to have parallel sessions now. So room 1 will be this room. And if you look at the schedule, there's an alternative link for room 2. So we'll start and go through rooms in a couple of minutes. Thank you. All right, maybe 1 minute to get everybody settled. Jacob, could you say something so we can make sure we can hear you?
Hello.
Okay, great. Okay, great. So let's get started then. So our next speaker, here at the University of South Carolina is Jacob Juillerat, and he's going to be speaking on widely digitally stable composite numbers.
Thank you. Also, thank you to the organizers for organizing this. It's really nice to have some talks under my belt as a 5th-year grad student, even during COVID. So thank you. So I'll be talking about widely digitally stable composite numbers. This is joint work with Michael Filsetta and Jeremiah Southwick. In 1979, Erdős proved that there are infinitely many prime numbers n with the property that you can change any digit in the base 10 representation of n, and the resulting number is always composite. These are called digitally delegate primes, and the first such prime is 294001. And Konyagan pointed out that we can get a similar result for composite numbers that are co-prime to 10. So in particular, the example 212159 satisfies this property. So you can replace any of the digits in here, and the resulting number will always be composite. And one thing to note is it needs to be co-prime to 10. It doesn't need to be co-prime to 10, but the co-prime to 10 is important to get intriguing results. If you drop the requirement that n needs to be co-prime to 10, then you could get examples such as this, which if you replace any digit besides the first digit, then it's going to be divisible by 5 still. And if you replace the 5 with an even number, it's divisible by 2. And if you replace it with anything else, then it's divisible by one of the numbers in the parentheses. So very unintriguing, uninteresting. But m can be anything, so you still get infinitely many of these numbers that aren't co-prime to 10 that still you can replace one of the digits and it still remains composite. So in 2010, Michael Filsetta, Mark Kozak, Nicole, and Selfridge proved that there are infinitely many composite numbers n with the property that you can insert any digit into the base 10 representation, and the resulting number remains composite. So key thing here is we're now inserting digits instead of replacing digits. And the first such number is 25011. That is, you can insert a digit 0 through 9 to the left of this number, to the right of this number, or between any two of its digits, and any of those insertions is going to result in a composite number. This year, Philosetta and Southwick went back to looking at prime numbers, and they show that there's a positive proportion of the primes n, such that you can replace any digit in the base 10 representation, including one of the infinitely many leading zeros, and the resulting number will be composite. So the new thing here is that including infinitely many leading zeros. And they called these widely digitally delicate primes, widely to represent including the infinitely many zeros. And the first digitally delicate prime, 294001, is not widely digitally delicate, since you can replace the second leading zero with a 1, and the resulting number is prime. And even though their proof was constructive, and so our proof will also be constructive, they couldn't find an example in base 10, just because the computation, our computers can't really handle that right now. So we jump back to composite numbers. We're going to combine the inserting with this widely notion. So we consider the case of composite numbers that are co-primed to 10, that remain composite when any digit is inserted in the decimal expansion of n, including between two of the infinitely many leading zeros and to the right of the units digit. We call these widely digitally stable composite numbers because the compositeness is stable when you make this kind of change. And we show that there are infinitely many widely digitally stable composite numbers. And as I said, our proof is going to also be constructive, but we don't have an example just because we would need to solve a whole bunch of congruences, find a number that satisfies all these congruences, and our computers can't really handle that right now. But if we move to base 2, this number, 6135559, is an example of a widely digitally stable composite number, meaning if you write the base 2 expansion down and then insert a 0 or 1 anywhere, including into the infinitely many leading zeros, then the result will be composite. And we can get a lot more examples in base 2 just by looking at Sierpinski numbers. Sierpinski numbers are going to take care of the inserting into the leading zeros, and then we just have a finite number of insertions to check. So how did we go about showing that there are infinitely many widely digitally stable composite numbers? We don't start with just any number. We're going to start with an integer n that looks like this, where little m and capital M are large numbers that we're going to determine later. And we're just going to, the way we're going to make a widely digitally stable number is we're just going to put requirements on the little n and the capital M. This looks like a number that has a leading zeros, then it has leading sevens, and then we're going to add this m to it. And we're going to require that m has k digits and let little n be greater than m so that we actually have a string of leading sevens. And we can do this because we're going to put congruences on little n, so we just take n to be large enough such that n is greater than k. And the way we're going to show that this is or make it widely digitally stable is we're going to construct a finite set of primes, script p, and restrictions on m such that inserting any digit anywhere will result in a number divisible by a prime np. So we'll actually know all the primes that are we will have a finite set of primes that any of the insertions will result in a number divisible by one of these primes. So why do we have this 7 in front? This 7 makes the leading sevens, and the reason we wanted sevens there instead of 1s or 3s or something is if we take 7 to be in P and we let m be congruent to 0 mod 7, then n is divisible by 7. So we start with a composite number, which is good because that's what we wanted. But also, if we insert a 0 or 7 into the leading zeros, it will remain divisible by 7. And if we insert a 0 or 7 into the leading sevens, it will also remain divisible by 7. So we've kind of taken care of inserting a 0 or 7 everywhere except for the digits that are affected by this m. And we'll get to the m later. And while we're here, we want capital N to be co-prime to 10. So we're just going to take capital M to be congruent to 0, 2, 4, or 6 mod 10, so that N is congruent to 1, 3, 7, or 9 mod 10. So it's co-prime to 10. So the way we're going to do this is we're going to break it into 3 cases. We're going to look at inserting a digit into the leading zeros, which we'll denote as capital N sub 0 to the k of x. So 0 representing that we're inserting into the leading zeros. K is telling you where we're inserting, what digit we're inserting, or what digits we are inserting a number between. And then x is the number that we are inserting. And if we are inserting into the leading zeros, then all we're doing is we're just adding x times 10 to the k, where k is in the leading zero, so it needs to be greater than or equal to little n. And then we're also going to consider the case that we're inserting a digit into the leading sevens. Same idea, we're going to let d represent the digit that we're inserting into the leading sevens. And if we're inserting a digit into the leading sevens, that's the same thing as changing one of the sevens into whatever digit d we want, and then tacking on another 7 at the front of this number. So we're going to tack on that 7 and then change whatever one of the 7s to the d. And k needs to be in the leading 7, so it's going to be between capital K and little n minus 1. And then the third case is just inserting a digit into M. By into M, I really mean into the rightmost digits that M is affecting, but it's just easier to say into M. So we're going to take care of some easy insertions. We already took care of 0 and 3 into the leading zeros and 7s. So if we take 3 to be in our set P, and M congruent to 1 mod 3 and N congruent to 0 mod 3, then for both the leading zeros and leading 7s, we get that if you insert a 2, 5, or 8, the resulting number will be divisible by 3 for all non-negative k. And the reason we're able to use 3 in this way is because 10 to the k and 10 to the m are just 1 mod 3. So we remove the dependence on k here with the prime 3. So we have taken care of inserting a digit 0, 2, 5, 7, or 8 into the leading zeros or 7s. And we know that if we do that, the resulting number will be divisible by 3 or 7. So we still need to take care of inserting a 1, 3, 4, 6, or 9. So we have 5 more insertions for both the leading zeros and the leading 7s. The way we're going to deal with each of these insertions is the following lemma, which is pretty long and ugly. So I'll try to reduce it down or explain it. So first off, let CP be the multiplicative order of 10 mod A prime with the GCD of 10 and this prime equal to 1. And this lemma is saying that if we take a covering of the integers where the moduli of the congruences depend on primes, where 10 has order the moduli mod that prime. So in particular, I have my notes that explain it very nicely. The modulus is dependent on having a prime pi such that 10 has multiplicative order C of pi. So for example, if we wanted to put mod 3 here in one of the congruences, then we would need to have a prime such that 10 has multiplicative order 3 mod that prime. And if there's only one such prime, then 3 can only appear once in the covering as a moduli. And so this puts restrictions on how we're going to create these coverings. But this is the main idea, create coverings with these restrictions. We need n to be congruent to this least common multiple of the multiplicative orders, so that this 10 to the n minus 1 over 9 is going to be 0, mod the prime. And then we're going to put restrictions on m so that when we look at inserting a digit into the leading zeros, the number will be composite. It will be divisible by one of the primes pi that is in our covering. And we will have a similar lemma to this when we are dealing with inserting a digit into the leading 7s. Particular, we'll just have n7 down here instead of n0. And then this m congruent to negative x times 10 to the bi will be negative d minus 7 times 10 to the bi, and then minus 7 times 10 to the n. To obtain primes p of a given order, we only need to look at primes p which divide the cth cyclotomic evaluated at 10. So in order to determine how many times a number can appear as a modulus in the covering, we sit there and we just factor some of these cyclotomic polynomials. And this was done in Magma and in Maple, predominantly in Magma and then checked in Maple. So for example, this is the covering that we used for inserting a 9 into the leading zeros. And looking at this covering, this is saying that 10 has order 2 mod 11, 10 has order 4 mod 101, 10 has order 8 mod 73, and 10 has order 8 mod 137. And there was only one prime, 11, that 10 has order 2. So that means 2 can only appear once in this covering. Going on, moving to the third bullet in the lemma, we want m to be congruent to negative x, which in this case we're dealing with x equals 9. So we have negative 9 times 10 to the k, or bi, which is in this case 0 for the first congruence, and so on, mod 11, 73, 101, and 137. So we have these congruences on m, and we have the other two congruences on m that dealt with 7, the prime 7 and 3. And so the main issue here is that we want such an m to exist in order to say that this number n exists. So we only want to use each of these primes once so that they appear in a congruence for m once, so that we can use the Chinese remainder theorem to ensure that such an m exists. And we want m to exist for all of the insertions. So while we have 2 in this covering, that means that 2 can't appear in any other covering because that would require the prime 11 to appear. And that would give us a different congruence on m, and m can't be congruent to 2 and 3 mod 11, so we can't use the prime 11 again. And just to reiterate, we are now adding these 4 primes to our set P. So now if we have inserted one of the 5 original digits that we had taken care of, or 9, then the resulting number will be divisible by one of these 6 primes. So moving to the next insertion. This was the covering used for inserting a 3 into the leading zeros. Notice we didn't use 2 because we can't use 2. But there was only one prime where 10 has order 3. And these primes are getting larger, like P2 of 54 was too large to fit in this table, and it still looked nice. And we also just have more covering and more congruences. And each one of these congruences is a congruence, or corresponds to a congruence on M. And this is where, like, yes, this is constructive. We are saying M needs to satisfy all of these congruences, but finding an M that satisfies all of these is getting unrealistic. And this was a covering for x equals 3. We still need 3 more coverings for inserting a digit into the leading zeros, and then 5 more for inserting a digit into the leading 7s. And the last covering that we used for inserting a digit into the leading zeros had 124 congruences. And the moduli got pretty large there. We were looking at moduli that were divisible by 11. So this M is getting unrealistic to solve for. But after we've done these 5 coverings, we have taken care of inserting a digit into the leading zeros. So we move to inserting a digit into the leading 7s. And the last one for inserting a digit into the leading zeros was 124 congruences, was looking at moduli divisible by 11. So these coverings are getting harder and harder to find. But since we're now moving to leading 7s, we can start to reuse primes. In particular, the fact that we have the 7 times 10 to the n, this is just going to shift everything like over 7, basically, with respect to the m. And we can now change what d is. So some of the primes can be reused. So for example, the prime 11, 10 has order 2 mod 11. And we used 11 in the covering for x equals 9. And there we had that m was congruent to negative 9 times 10 to the 0, which would be is congruent to 2 mod 11. Looking now at inserting a digit into the leading 7s, if we let k be congruent to 0 mod 2 and d equal 9, then because of this 7 times 10 to the n, n7 of 9 will still be congruent to 0 mod 11 if m is congruent to 2 mod 11. So we can reuse the prime 11 as long as we use exactly this covering congruence, k is congruent to 0 mod 2, and exactly the covering that deals with d equals 9. when we were doing this, we were able to reuse 14 primes. We were able to reuse a lot more than that, but some of them weren't useful. So we used 14 primes again in 16 different congruences. And it doesn't sound like a lot, but when you get like k is congruent to 0 mod 2, that's half a covering. So this greatly reduced the amount of work we needed to do. So we did 5 more coverings for leading 7s. The last covering took over 300 congruences. So this M is getting very unreasonable to solve. So now, with those 10 coverings, we have taken care of inserting digits into the leading 0s and the leading 7s. So I move to the last case, which is inserting a digit to the rightmost digits, which I said is basically M. But now that we have all those congruences on M, we're just going to fix such an M that satisfies all of those congruences. Since M has a fixed length, there are only a finite number of insertions when inserting a digit into the rightmost digits. And that's because it's finite length. You can only insert a 0 through a 9, so a finite number of insertions. So the idea behind dealing with the rightmost digits is make one of these insertions, and then the new number that you get, take the least prime, qi, that divides it, and then just add it to our set p if it's not already there. The problem with doing that is if the number itself was prime, then you might just have a number like that insertion would result in a number larger than capital N. So we need to make sure that capital N is larger than this least prime. So we're just gonna make it larger by letting little n be congruent to 0 mod. All those LCMs that we had before, we now just tack on this new order of 10 mod this prime. And that'll make capital N large enough that it's larger than this qi, so it's now actually divisible by it instead of just equal to it. There are infinitely many such n that satisfy this congruence. Therefore, we have infinitely many widely digitally stable composite numbers. So what's next? What could we do with this? Can we find an example? I don't know how great quantum computers are, but maybe a quantum computer could handle this kind of computation. Not sure. Can we show that there are a positive proportion of widely digitally stable composite numbers? Philosetta and Southwick were able to do this for widely digitally delicate primes. Can we do that here? I think this is doable. I don't think it's going to be too hard. And then are there infinitely many widely digitally stable composite numbers that remain composite when we replace any digit? So that is, can we insert a digit or replace a digit, and either of those will always result in a composite number? And then can we extend this to the primes? The primes were replacing a digit. Here we are inserting a digit. So can we insert a digit with primes? And thanks for listening to me. Any questions?
Great, thank you very much. Yes, any questions for the speaker? All right. Okay, so if there are no questions, so there's a question from Alex Clifton. So was all 7s instead of all 3s because it's harder to change something to a 7?
It was all 7s instead of all 3s. I don't want to scroll back because that's a lot of scrolling. Because if we had all 3s, then we would have to use 0 congruent to, M needs to be congruent to 0 mod 3, which would get you 0, 3, 6, and 9. But then we wouldn't be able to use 7 to get a full covering. So we weren't able to use 7 to get a full covering. I think 7 had, I don't want to think about what it is because I know I'm going to get it wrong. But the 10 has multiplicative order, something a little bit larger with 7. So we would only get like half a covering or a third of a covering with that. Whereas when using the 7 with the leading 7s, we were able to take care of inserting a 0 or a 7. So 2 full coverings. Initially, I was going to do leading 9s instead of leading 7s, but that was even worse.
Okay, great. Any further questions? Okay, so let's thank the speaker again. I guess where's the clap emoji? There we go. Okay, so we meet again in parallel rooms in 6 minutes. Thank you.